So welcome everyone for joining tonight. In this session, we're going to do a bunch of practice problems, and I just want to focus in on implementing technology to solve a bunch of these problems. So from chapter about 6, or actually 7, all the way through the end of the course, it's all automatic from this point. So you should not be spending a lot of time working these problems out. At this point, we should be able to um, use the technology to actually do a bunch of the problems. So I got earlier today, I got a message about chapter 8. So I do want to jump there, and then also I wanted to spend some time with the z-scores as well. That was a little confusing for some. In fact, maybe we should start with the z-scores first and then work our way up, um, because I think understanding the z-scores and problems from chapter 7 will help us quite a lot. And it's only 2 sections in chapter 7, 7.1 and 7.2. 7.2 is really the meat of chapter 7. 7.2 is probably going to have the most questions on the final exam. So 7.2 to me is extremely important. Um, it also hypothesis testing. Okay, that's something that you have to be able to know how to do, and you have to be able to know how to use your technology to do it. Because you don't have to calculate certain things out by hand. All right. So the first thing we're going to get into is let's look at the normal distribution. All right. And this isn't just the normal distribution. This one is called the standard normal. I'm going to put standard in quotes because some of them don't have that distinction. And let's talk about that real quick. Now, when it's standard, that means that the scores are standardized. And now the scores are all converted into z-scores. So whenever you're dealing with a z-score, you are dealing with the standard normal distribution, which basically means that the mean is 0. And the standard deviation is 1. And so I'm going to make this shape here. The, the standard normal distribution is a bell-shaped curve. And I'm going to put down here that the mean is 0. In fact, I could even say the population mean. The population mean is 0. And little s stands for the sample deviation. That's 1. And I can put it in the population. Little sigma is 1. So that's what it means to work with the standard normal distribution. And all of these scores, I'll put in -1, -2. These are a deviation. These are the z-scores. Okay, and another thing about this, what we realized is that the standard normal distribution is also, it doubles as a probability distribution as well. Okay, so I'm going to add that too. It is a probability distribution. So there's really two things going on. On one hand, we have a bell-shaped curve, normal distribution. All the scores are standardized so that the mean is 0 and the standard deviation is 1. But also, it turns out that it is a probability distribution, which basically means that the entire area is 100%. or one whole. And so now we can make the connection between finding the area of probability z-scores and whatnot. So there's going to be a lot of questions about this. Let's look at some of the questions. One of the questions could be find, in fact, hold on, let me make sure that so there's two things going on with this. It's a standard normal distribution, and it's also a probability distribution. And so what we could do is say, here's an example. Problem could say, find the probability of selecting I'll put selecting a random z-score between 1 and 2. What is that probability? In other words, and we can highlight it here, this portion, if I were to randomly select a z-score, what is the chances that that z-score will be between 1 and 2? That's one way to ask this question. Another way to ask this question would be, what is the probability of, or what's the proportion of the entire normal curve between 1 and 2? What's the proportion? We know the whole thing is 100%. So there's a bunch of ways to solve this problem. This is considered a normal CDF problem. And what we would do is put in the lower bound, which is 1, and we put in the upper bound. And then the normal CDF command will accept the mean. The mean is 0. And the standard deviation is just 1. And that will give us the area. It's probably about 16% or something like that. This is a common, that little sector is about 16% or so. We could pull up our technology and see. We go to second distribute, and it's number 2. We never use number 1. We put in our lower bound, our upper bound, go down the paste. Okay, we're getting 13.5%. That's fine. That's fair. So that's kind of the gist of the kind of questions that they're asking. Sometimes, though, they'll say, they may give another type of question and say something like, hey, what's the z-score if this area to the left is, let's just say, the area to the left is, say, I'll just give some random number like 30%. What's the z-score? This is another type of problem. Now this time we don't have the z-score, but we have the area, the proportion to the left. And so instead of using normal CDF only works when you have the z-scores and you want to find the area. We have to do the opposite. We go to second distribute, and this time we have to use inverse norm, number 3. We put in our area, it's 30%, and it has to be the area to the left. And that's it. Our mean is 0, deviation is 1, so it's the standard normal distribution. And our z-score is negative 0.52. All right. We can look at some problems. Oh, 1 second here. Let's look at some problems from chapter 7. Yes, absolutely. The TI-83 and the TI-84 use the same steps. So you're absolutely right. It's second distribute. That's going to be the way to go. That's where you're going to find all those stat functionality there. Let's jump into 7.2. Yeah, that's a that's a good point. That's a good point. For the TI-83, you might not have Stat Wizard. So, like, let me go into mode. If I go into mode, I have this thing called Stat Wizard, which prompts me, so I don't have to remember the parameters in the order. It prompts me to enter in this stuff, but if I actually took it off, now if I go to second distribute, and choose number 2, it's going to give it to me on the home screen, and I have to know what it needs. And so that's the difference. Your 83, I'm thinking, might not have it. I think it's the 84 that has the Stat Wizard. You might want to check under mode and see. Okay, so it will accept 4 things. If it's the standard normal distribution, it will accept 2 things. So like if I put 1, 0, or 1, 2, it's understood that it's the standard normal distribution. So it will accept this and do it. But usually, sometimes we don't work with the standard normal distribution. So we have to put in all 4 things. 1, 2 is the lower bound, the left bound, the right bound, because we want to find the area in between. And we also have to put in the mean and the deviation. So that's what it will accept. And you're good there. Okay. Well, the calculator will only be left. Exactly. Yeah. Always left. And when you have to find the area to the right, you know the technique. So if I put in 0.3, or actually 0.3, yeah, you're right. I mean, it would be. Or you could subtract it from 1. There's tricks to do that, and we can look at some problems. But also, inverse norm will accept 3 things as well. Let's go there. Um, the, the area to the left, and then your mean and your deviation. I just happen to know. It will. This is the order. Um, I just happen to know that. That's the one thing about this, is that you'd have to know. You cannot mess this order up. It won't give you the right answer. Now, yes, and StatCrunch will do it as well. And we can go to StatCrunch and take a look. Let's dive into to section 7.2 and look at some of these problems. Maybe we could also go to 7.1 as well. Start there, but let's just see the kind of problems that they're giving us for 7-1. The final is cumulative. However, there will only be a few problems, probably less than 5 problems from the past. The majority of the problems will come after. And on Thursday, I plan to have another session and talk a little bit more about the final. I want to talk about the sections that will pop up. And then also we're going to talk a little bit more about the practice final, going over the solutions to the practice final. So in this homework, 7.2, this question, it might be kind of small for you guys to see, I don't know, but it says determine the area under the standard normal curve that lies between negative 0.25 and positive 0.25. And so we're talking standard normal, which means that the mean is 0 and the standard deviation is 1. And so this would be a normal CDF type of problem. And they want you to round to 4 decimal places. And so it's just it's a matter of just I'm going to clear this out. Going to second distribute, number 2, putting in negative 0.25 and positive 0.25. I could put 0 and 1 as well, but since it's standard normal, by default, it will do it for me. I could just put my lower bound, upper bound. I'm getting 0.1974. Uh-oh, wait, did it not? Wait, what just, let me go back. That was weird. I had more parts to the problem. All right, now look at, oh, did I click similar question? Okay, well, let's do this one again. Let's do another one. And this problem says the area that lies between a z-score of negative 1.62 and a positive z-score from 1.62. And graphically, what this looks like would be, I'm going to use some kind of marker. Negative 1.6, what was it? What did it say? Is it 1.62? So that would be approximately here and here. And it's this area. We're about to find this area, which is a good portion of the normal bell-shaped curve. The whole thing is 100%. So we are probably going to get about 80% or so. Okay, it's almost, because from negative 2 to positive 2 is 95%. So we might have about 90% or so. So what I'm going to do is go into normal CDF. I could do a second entry to recall that, and then put in negative 1.62 comma positive 1.62. I could put in a 0 and 1, and I'm getting 89.48. They wanted me to round to 4 places, so 89.48 should work for this. So I'm going to put that in, 0.8948, and then I hit, let's see, do I hit next? Will that take me to the next part? It takes me to the next question, but I wanted to get to the next part, which is kind of odd. Let's see here. Okay. I'm gonna do the same problem now. I think you guys are able to follow. This one's actually relatively easy once you get the hang of it. You're giving your lower bounds and upper bounds. So it's really just a matter of plugging in your lower bound, your upper bound, and since it's standardized, your mean is 0 or standard deviation is 1. Let's do the same problem, but this time let's use StatCrunch. So get more help under StatCrunch. It should log you straight in. You go to Stat, Calculator, and it's the normal calculator. So my mean is everything. We need to find between two z-scores. So my two z-scores are going to be negative 1.72 and positive 1.72. Those were the two. Oh wait, was it 6? It was 6.2 before. Compute. It was 89.48. And it gives you the picture, the diagram of the area that you just found. So I chose between. Sometimes they'll say to the left, or sometimes they'll say to the right, or sometimes they'll say in between. And in the graphing calculator, this is the normal CDF command. Will give you all of that. In the calculator, you'd have to just put a very large number for your upper bound, like 1,000 or something like that, some large, any number past 10. But it's best to put in like 1e to the 9. That's what you probably have seen for your upper bound. Or if it's to the right, you'd put in some extremely tiny negative number, like -1 to the negative a billion, or negative 1e to the 99 power in scientific notation. And then your upper bound would be, in this case, 0. And it would be 50%. Half of the normal bell-shaped curve is exactly 50%. So 7.2 and 7.1 is all about mastering the normal bell-shaped curve. And we have two ways to do it now. Okay, you can use your calculator, or you could use your StatCrunch. So let's look at a couple more. These looked a little easy. I'm trying to see if we could find one. Determine the total area under the standard curve from parts A through C. So find the area under the curve to the left of z to the -2 plus the area under the curve to the right of z equals 2. Now, what we could do is find the area in between 2 and -2 and then subtract that from 100%. That's getting a little slick. Let me show you visually what that a way to do that. We already know from -2 to +2 is 95%, approximately 95% of the whole thing. They want us to find, and this is the standard normal curve. There's -1, 1, 2, and -2. They wanted us to find this area in the two tails. Our calculator won't do it. It will have to do the problem twice and add it together. Our calculator does to the left and to the right and in the middle, because our calculator knows that that's enough. Anything, if you need anything else, you could do it on your own. And so one way to do it automatically would be to find the area of the middle, which is easy to do, which should be about 95%. Let me confirm that. Let's do a second entry. And this, actually, we should have just, let's just start a new one. And let's just go from -2 comma to 2. It's 95%. If I subtract that from 1 minus the last answer, I'm going to get 0.0455. Okay, they probably want it to 4 places. So 0.455 would be sufficient. That's one way to do it. The other way is to do one tail and double it, because it is symmetrical after all. Or just do one, do the other, and add it together. But it's not, StatCrunch is not going to give, there's no logic that's going to give you the outer tails like that. But this is important though. There is a need to know this. They're not just giving you this work for no reason. Sometimes it is important to understand how much is in each tail. Okay. So if I put in the combined area 0.0455, I want to be able to check that that's right. So I'm going to click Let's see, just enter. I don't know why it's acting really weird for me, but if I go back, let me see if I go to the homework list. Actually, wait, let's see. It's like it's not counting it. It's not counting what I'm doing, which is kind of rare. But you guys can try it and verify as well if these are some of the problems. Now here's another one. Now this time it's different. So we were given the z-score before. Let me make this a little bit bigger so everybody can see. Sometimes it's best just to go straight into StatCrunch because then you'll have the full screen. I'm gonna do that real quick. You just click on that yellow button and get in there, and now I'm just gonna go to assignments and find 7.2. Improve the score. Oh, because I clicked review and practice, so I should have clicked improve score because now I will get graded. So I didn't realize that. That's good to see. Okay, we know this one. The combined area was 0.0455. Check. We got it. Okay, find the area under the normal curve to the left plus the area under the curve to the right of z 2.55. Okay, I can find the area in between them and then subtract from one whole, 100%. I could do it that way, or I could just find the area to the left and then find the area of this portion and combine it together. Okay. And so let's do this, and then we're going to do one with the inverse norm. So this time what I'm going to do is find the area of both in between, and then I'm just going to subtract negative 1 point, oh, negative, let me see, hold on. Trying to get my everything up. Okay. Okay, let's see. Where was I? I needed that. Okay. We're going from negative 1.55 to 2.55, I believe. Okay. This is going to be the area in between. Now I'm going to subtract that last answer from 1. And I'm getting 0.659, but when you round it off, it's actually going to be 0.660. Find the area under the curve to the left of this, plus the area under the curve to the right of that. Alright, well I'm going to use StatCrunch this time. I think I already had it up. Alright, where do you go? Well, it's usually stats is where you go for everything. And you have to go to the calculator. It's usually either calculator or summary stats. But since this is the second half of the course, most of our stuff will be in this calculator, or sometimes it could be the z-stats or the t-stats or even regression, or maybe proportions. Those are our options. We won't be using ANOVA and all of these other time series stuff. That's good stuff, but we're just not going to be doing these kind of statistical tests. Okay. But in our case, for the normal calculator, we need to go into calculator and normal distribution. That's the kind of distribution we have. We have all kinds of different types of distributions. There are many different types of distributions. The Poisson distribution. But in our case, we're working with the normal distribution. And I want to calculate the area in between the two. and then what I'm going to do is subtract out. So negative 2.23, and the area to the right is 1.3. And let's make this a little bit bigger. Whoa, that's really big, but that's the portion. But the problem is this is not what we wanted. It's not what we needed. It is what we wanted though, but what we need is to get the area to the outside region. And so the trick is to subtract this piece, the red piece, from 1. So we have to do 1 minus this number. I don't even know if it will do it all, but I'm going to copy it into this. I won't do it because I didn't round properly. So I'm gonna we need to pull out our calculator for this. I'm going to do 1 minus 0.49. I'm going to use a lot of decimal places, all of them. 4941, 53. What was that? 63. We don't want to get a round off error because now we're going to round this off. If we rounded this off and round this off, our answer could end up being wrong. So we want to be as accurate as possible. Now we got 5058. We're going to plug that in there. And it worked out. Okay, now this is the other one that I want to get to. So it came up. It says find the z-score such that the area under the curve to the left is 0.28. So we don't have the z-score. We have to find it, but we do know that the area to the left is 0.28. And so for this, we don't use normal CDF, we use inverse norm. Number 3, we put in the area to the left, which was 0.28, and that's it. It's going to give me the z-score. I could have put in comma 0, comma 1 as well, but that's my z-score, and I need to round it to just 2 places, I believe. Usually z-scores are rounded to 2 places, so negative 0.58. That was it for that. The approximate z-score that corresponds to a right tail area of 0.22. Well, look at this problem. They want me to find the proportion, the z-score. I'm just going to use the same chart. Find the z-score such that the area to the right of it is exactly 0.22. Well, the inverse norm only works for the area to the left. This is the dilemma. All right, my z-score is right here. I don't know what it is. This is just an approximate drawing. I don't know. 0.22 could be a little bit more to the right, but or maybe this is a good one. But it's probably between 1 and 2. But the problem with this is that the inverse norm only works for the area to the left. So what we have to do, what we could do, there's other ways to do it, but we could subtract 0.22 from 1 to get the area to the left. The area to the left would be 0.78. So now we're going to just do inverse norm. Okay, hope you guys with me on this. I don't want to lose anybody. We're going to do inverse norm of 0.78. And guess what? That's going to be our z-score. 0.77. That's what I'm going to put in there. So it wasn't more, let's see, it wasn't more than 1 at all. It was less than 1. And StatCrunch would have been able to do it as well. Okay? StatCrunch would have done it. Okay, now we're not working with the standard normal distribution anymore. We're working with a normal distribution, but the mean is that the scores are not standardized. We can standardize them by dividing by the mean and or subtracting from the mean, dividing by 7, we'll standardize it. Like we could standardize 40. It'd be negative 10 over 7, and that would be the z-score. But we don't need to do that. That's when you had tables back in the day, when you had tables and the tables had all the z-scores and you had to look it up. But now we have technology, so there's no need to do it. We don't need z-scores for nothing, other than to use the tables. That's really the big picture behind them. That's the history behind the z-scores. But now we were just, compute is cheap and powerful, and we can just immediately find it out. So anyway, this problem is saying assume the random variable x is normally distributed with the mean of 50 and standard deviation of 7. Compute the probability and be sure to draw a normal curve with the area corresponding to the probability shaded. So this should be read as the probability of x is greater than 40. So what is my chances of selecting some random number and it's greater than 40, right? Or let's say I'm throwing a dart at this shape. What's the chances of my dart landing in an area that's greater than 40? The scores are below. Majority of the scores are in the middle. All right, this is a normal distribution. There's a lot of things in nature that follow a normal distribution. Almost everything in life has aspects of it. It's not necessarily perfect and theoretical, but there is aspects of that normal distribution. All right. So anyway, I'm looking for a chart that has, is it only 3 choices? I would go with this one. The reason why is because this looks like all the scores are below, and these are all, the things that shaded are all the scores greater than 40. Now part B, what is it? What's the probability? Which is actually the area. Because it's a probability distribution, we can interchange it. We can talk about probability, we can talk about area. It's all the same thing. So basically, this is a normal CDF problem. My lower bound is 40. My upper bound is some gigantic number. All right, my mean is 50, my standard deviation is 7. So this is what we're going to do. We're going to do this problem. We're going to go to distribute, number 2. My lower bound is 40. My upper bound, I'm going to put 9e to the 99. That's 9 times 10 to the 99 power. That's extremely large. My mean is 50, and my standard deviation is 7. My area is 0.9234. Now, I should have mentioned that we could have actually, we'll do one more, and this time we'll use StatCrunch. All right, so this time, same thing, different mean, different deviation, and they want me to find the probability of everything less than 44. Looks like C. We could blow it up, make it look a little bit better. That definitely looks right. All right. Now, for StatCrunch, we don't have to put in a lower bound, upper bound. We can just immediately find that region by going into our calculator, normal calculator, and we're going to find that standard area. The mean was 46 and 10. We got, so, and this time, I don't know, I keep forgetting the numbers, 44 and less. So we're talking area, all the x values. What's the chances of getting all my little x values, which are my random, my random numbers, less than 4, 44. I have to hit compute. I'm getting 4207. So now we're going to plug that in. 0.4207. 4207, and it works. I think we're almost done with this assignment. We've done so many of them. Okay, here's another one though. This time they're saying what's the probability of getting an X between 56 and 68? Our mean is 50, deviation 10. It would look something like B, first of all. And secondly, we simply use normal CDF here. We don't have to do anything weird. You don't got to do anything more than that. It's just this is it. You plug it in and you're good. Make sure you round to 4 places. They always want the area in 4 places. The proportion, or whatever. When they say 4, you put 4. Let's look at a couple more. Find the 96th percentile. Well, and we're talking mean 50, deviation 7. Well, let's look at that for a second. Deviation is 7, so this will be 57. This will actually be 43. I'm subtracting 7 from each one. We could add another 7 to this. That'd be 64. Subtract another 7. That's going to put us at 36, I believe. The question was, find the score that's in the 96th percentile. That's going to be approximately here. The area to the left is a percentile, and this area is exactly 96%. So this region right here, we need to find that. This is an inverse norm problem. We do inverse norm we do hold on. We do the area to the left is 0.96. .96, comma 50, comma 7. And I'll show you how to do this on StatCrunch as well, guys. Let's make sure we got the same answer. Then we're going to move on to another topic, unless there's any other questions. But let's go to inverse norm here, number 3. And this time I'm going to choose 0.96 because that's our percentile. 50 and 7. Let's double check this. It's going to be 62.25. Let's see if StatCrunch will give us the same thing. I think I just lost that window. There's now for StatCrunch, you got the same thing again. All right, we're talking area to the left, so you got to put in the area first. 0.93 or 0.96. You do have to put in the mean and deviation, and it's going to give you whatever's missing. So that's how this works. 62.25. I got that twice. It must be the answer. So we plug it in and see. 62.25, and it works. All right. Any more questions on that? So percentile is nothing more than area to the left. It's just a fancy way of saying you have the area to the left, give me the score. Yeah, so inverse is whenever you have the area and they want you to find the score or the z-score, then that's your inverse norm. But when you have the score and you have to find the area or you have to find the probability, that's normal CDF. So it really just depends on what you have, what they gave you in the problem. Okay? So this is actually a pretty good problem. They're basically saying that um, they're talking about the chips, the actual chocolate chips, um, have a mean of 1262 and a standard deviation of 118. And part A, it says determine the 29th percentile for the number of chocolate chips in one of these bags. And so for this problem, this will be an inverse norm because they gave us the percentile and they want us to find the number of chips, which is the X value. Same thing for part B. Determine the number of chocolate chips in a bag that makes up the middle 97%. Okay, that's actually kind of a trick question. The middle 97%, StatCrunch can do it, but our calculator cannot. StatCrunch can do the middle 97% for us, no problem. Let me demonstrate this. You have to hit between and then just do 0.97. And then at that point you put in your mean and deviation, 1262 and 118. And it's going to be between 1005 and 1518. Now the way we would have had to do this on our calculator, we would have had to find the area to the left and find the z-score with inverse norm, and we would have had to find the area to the left of this portion, and then we would have gotten the two bounds that way. But with StatCrunch, it actually was able to do it pretty quickly by choosing the between and putting in, we were talking about the inner 97%. So that was a pretty good problem. And that was part B. Let's see. Oh, there's only 10 questions? Okay. Yeah, there's only 10 questions. Not too bad. Not too bad. Any other questions on chapter 7? Because I was thinking about moving on to another chapter. But if you guys have another chapter or another problem from chapter 7, that would be great. On 7.2? Okay. Oh, make sure that you are using, for your negative, you have to use this button. So you go to second, distribute, number 2, and you have, does it look like this at all? Do you see my screen? All right. So I need to put in my lower bound and my upper bound, my z-score. So my z-score is negative 1.57. So you don't put minus, you got to put the negatives button here, negative 1.57. Actually, it's, let me try that over. Second distribute, number 2, normal CDF, and I have to put in negative 1.57, comma, positive 1.57, and that's going to give it to me. If I did minus, if I used the subtraction button, I would have gotten an error. And sometimes they'll tell you what the error is. Um, does that clear it? Oh, okay, yeah, no problem. Um, let's see. I think so. You know, just because I think that especially if you have StatCrunch up and running, you don't have to go back and forth. And then we also saw the power of StatCrunch where it has that in-between mechanism, especially for areas in between. I'm surprised they even asked us that question. But with StatCrunch, I was able to solve it right away. But yeah, I mean, once you got the hang of it and you're comfortable with either or, to be honest with me, it was my students that got me into StatCrunch. I was always leery of it and skeptical, and I didn't even want to have to learn something new. And then all of a sudden, I started getting StatCrunch questions more and more as I taught over the semesters. I started teaching the class more and more, and more students would ask me questions about StatCrunch. And so I had to help them through it, and I got into it. And now it's like, yeah, StatCrunch, use it. You know, it's okay. It's accessible. You will have access to it on all the quizzes, and you have it on the final, and it could help you through it. So so it's possible to get through the course without having a graphing calculator. So, but we still say use a graphing calculator because it's traditional, and some people may feel more comfortable using that. And so that's one of the reasons why we still require the graphing calculator. But yeah, that's a good question though. Yeah, so there were some questions on chapter 8. Um, and so, yeah. Mm-hmm. All right. Yeah, let's take a look and see what's going on there. So you said, hopefully mine's is just like yours. So 8.1, and you said question what? Okay, okay. And this actually has 9 parts too. So this is a gigantic problem. But we do know that pregnancies are normally distributed, approximately. The mean is 266 and the standard deviation is 16. So the first thing we're going to do is create that bell-shaped curve just to get a feel for the shape. The mean is right smack in the middle. That's probably 9 months, right? I didn't do the math on that. And then the deviation is 16. So if I add 16 to this number, I'm going to get 282. If I subtract 16, I get 250. And so on and so forth. Now, this is what our distribution looks like for pregnancies, okay? For part A, what is the probability that a randomly selected pregnancy lasts less than 261 days? The probability, less than 261 days. So the z-score, or the score, is 271, or 261, I should say. So we need to find this area here. This will be the probability. So it is a normal CDF problem. We're just going to use normal CDF. My lower bound, I got to put in some negative number, some tiny negative number. Negative 9e to the 99. It doesn't have to be that extreme, but we just need something very, very. I mean, after 200, after 100, it's going to be fixed. I could put in 0 as well, but it's okay. The upper bound is going to be 261. The mean is 266, and my standard deviation is 16. So we can use, this is for the calculator command, but we can also just use normal CDF. So that's what I'm going to do. Let's use that normal CDF and get this problem real quick. So I'm going to do the standard. Our mean was 266, deviation 16, and we're looking for pregnancies that last from 261 on down. So the probability of this happening is 3773. One second. Was that clear? Any questions there? Yeah. We didn't even have to. Yeah, that would have been a pain. And it's unfortunate that they did it in that direction. Let's see. Let's keep going here. It says to interpret this probability, select the correct choice below. If 100 pregnancies were selected independently from this population, we would expect, I would say, about 37 pregnancies out of 100 to last less than 261 days. All right, let's see some of the other choices. If 100 pregnant individuals were selected independently from this population, we'd expect to last exactly 260, or expect it to last more than 2. Well, this was for less than 261. So I'm going to say, it said round to the nearest integer. So I'm going to say 38 pregnancies to last less than 261 days out of 100. Okay, so now it's going to start to get a little weird now, because in chapter 8 we're dealing with the sampling distribution, and I remember making a video about this recently. We cannot use that normal distribution to answer this question. We'll need a sampling distribution. And let me explain the problem why. So the problem says, suppose a random sample of 22 human. They're making it so you could tell this is a male who wrote this, right? Okay, I shouldn't say that. Suppose a random sample of 22 human pregnancies is obtained. Describe the sampling distribution of the sample mean length of pregnancies. Alright. Well, we're dealing with a sample of 22. And so in order for us to figure this out, we have to use samples of 22. There has to be an awful lot of those samples. So that's the way this works. And then what we learn is that the sampling distribution, the mean of the sampling distribution is equal to the population mean. They're actually the same. And it's a result from the central limit theorem that proves it. So it's actually a work of art, the fact that the sampling distribution of all of these samples. So in other words, if I take a sample of 22 pregnancies and calculate the average, and then I get another sample and calculate the average, and I get like 1,000 samples of 22, random samples of 22, to create a sampling distribution of just only 22, and I were to average all the averages, it's like the GPA, like the average of the average. The average of all those averages would be equal to the population average, which is 266. So the sampling distribution will be normal, and the mean would be equal to the population mean. The deviation will not. Now this is where the deviation will not be 16. This is where they depart. The sampling distribution will have the same mean. It'll be symmetrical, but you'll actually have to calculate this little distribution mean there. And in order to calculate that, all you need is just a formula. And the formula is that you take the original deviation and divide by the square root of the sample size. So it's 16 divided by the square root of 22. 3.41. Now, for some reason, they're saying type integers or decimals rounded to 4 places. So if they want more places, I'll give them a couple more places. Let's check this. It worked. So for this one, you do have to have that formula down. So now we can answer questions about a random sample of 22. And remember, the sample of 22, of size 22, that's a tiny sample. It's coming from the population randomly. So now the question is, what is the probability that a random sample of 22 pregnancies has a mean pregnancy period of 261 days or less? Well, we do normal CDF, but this time we're going to use the mean at 266, and the same mean, but we're going to use the deviation of 3.4112. Our lower bound will be some negative number, our upper bound will be 261, and we'll get it. We just have to use a new deviation. So in other words, I mean, I literally could pull up our calculator command, what we just did. We could even go to StatCrunch and just change this from 16 divided by the square root of, I don't think they'll, well, then let me, no, I'll just put 1 point, it was, what was it, 3 point, And what we're going to get is 0.0716. 0714. And now it's time to interpret this. If 100 independent random samples of size 22, all the samples are the same size, and we're taking the average of each of those samples, we would expect 7 of those samples to have a sample mean of 261 days or less. Actually, I'm going to go with this one instead. And another question: what is the probability that a random sample of 72? This is different. We need a whole new sampling distribution of sample size 72. We don't know anything about the first distribution was the full population. The other distribution was all sample sizes of 22. This time, they're asking us what's the probability that a random sample of 72. So we need all of the samples of 72 possibilities, which is almost infinite. It's as big as the population because we're taking random samples of 72 women from the population. We can generate millions of samples. And if we take the average of each of those little samples, we will get a normal distribution. We will get our sampling distribution. So the sampling distribution comes from the average of all those samples. And basically we just divide by the square root of 72. The mean will be the same, it'll be 266, but the deviation of this will be 16 divided by the square root of 72. The distribution will be slightly different. It'll be more narrower. The deviation, the values will be closer together. Oh yeah, so that's a chapter 8 thing, and that's a good question. Let me go to, let's see here. That's going back into the course, and actually, like if I were to pull up the notes for chapter 8, it's probably one of the first things that you'll see. Well, these aren't really the note. This is more of the workbook. Okay, let me see. Oh, they have it here. It's a tiny little, that formula right here. The standard deviation of the sampling distribution is the population deviation divided by the square root of the sample size. It comes from the central limit theorem. It proves it. So it's just a formula from the book. Here it is again. Yeah, this is more formal. So if you start taking samples and averaging out each one of those samples, the average of those will form a normal distribution, and the average of the averages will be equal to the population average. The deviation will be smaller though. Okay, it'll be the population deviation divided by the square root of the sample size. So that's how that works. We're just using this formula here. The sampling distribution. So that's it. It's really chapter 8 is just like chapter 7, except your deviation for the sampling distribution is little sigma divided by the square root of the sample size. So other than that, it's pretty much the same type of chapter. And I created a video on this recently. Someone asked about a homework question, and the video went a little longer than I expected. It was under the helpful random homework problem video set, which is also links to my YouTube channel that has some statistics. And this was the problem. It was homework problem from 8.2, number 5 and 6 using StatCrunch. Well, it looks like I did a problem. I did a problem. I did number 6 and part of number 7. But also I have a video here, and this is the last video that I have for the helpful homework videos. But in this video that I recently I made this about a week ago. In this video, it's a 20-minute video, and I go over quite a lot about what I just explained now. But this is for proportion now. We just did with the mean. So 8.2 is proportion, not the mean. So I did a few problems from 8.2 right here, trying to work them out. So I explained the sampling distribution. So p hat is a sampling distribution. So we just start taking a bunch of samples of size 500. And you just take more and more samples all the way down. You just take as many samples as you can. All the possible sample sizes of 500. It's almost infinite, but it's finite. Because remember, some of the samples will even have members from the other sample in them, because they're random. They could end up in the same sample. You're just randomly taking samples, and some of they're not all disjointed. Some of the samples could have like if we had pregnant women, some of the pregnant women could be in another sample, a different sample. But we're still taking averages of all these random samples, and the averages of all the samples turns out to be normally distributed. And the average of all of them is equal to the population average. It's a little magical. But yeah, so chapter 8 and chapter 7, they're not so tough once we see the other way to do it, the technology way. All right. Now 9 and 10. 9 is where we get into the hypothesis testing. Yeah, let's go to it real quick. So I just pulled up 8.2, and which one was it? All right. Okay, and so let's read it. It has multiple parts, so this is a big problem. It says, according to a survey in a country, 35% of the adults do not own a credit card. So that's the proportion. In chapter 8.1, we're using the mean, right? Let's say the average of such and such. But in 8.2, we're talking about a certain proportion. That's fine. Suppose a simple random sample of 700 adults is obtained. Complete parts A through D. And so we already know 35% of a certain country do not own a credit card. Now we're going to take 700 people, random sample. The sample doesn't have much bias. It's a good sample. 700 adults from that country. And now we're going to proceed. Now, before we get into anything, we have to make sure that these conditions are satisfied. Describe the sampling distribution of p hat, which is all the different samples of 700 from the country. So not just one sample. We're taking all the samples. Do you realize it's trillions of samples? Especially if it's a country of 1 million people, and we're taking different samples of size 700. It's going to be more than, it'll be more than 700. It'll be more than 1 million samples. I think that the amount of samples will be more than each member of the population, because the samples can be reconfigured. And this sample size of 700 is extremely large. So the sampling distribution will be approximately normal, and this all comes from the textbook. The sample proportion of adults who do not own a credit card, it will be approximately normal. And also the other condition is n is less than the sample size was n is less than 5% of the population size. And then also the third condition, there's 3 conditions that need to be met in order for us to do the magic. It has to be, or it will be, approximately normal. This needs to be met, that the sample size, little n is the sample size and big N is the population size. And then also that the sample size times the proportion, 35% of this little sample size, times 65%, 1 minus p, which is 65%, must be less than 10. And so I like that. I actually not less than 10, but it should be greater than or equal to 10. So I actually like this one. Approximately normal. Sample little n is less than 5% of big N. And also the sample size times the proportion, population proportion, times 1 minus this is greater than or equal to 10. That has to hold true. And now we get down to business. So here it says, determine the mean of the sampling distribution. So if we take all those samples and calculate the amount of people that do not own a cell phone in each sample, or not a cell phone, credit card, it will be around 35, 36. So some of the samples will be 36. Maybe we might get a sample that has 40% that don't have a. We might get another sample that has 30% inside that sample. We'll get different samples. Each sample will be slightly different from the other sample. Maybe some of the same samples will have 35%. But it turns out that the mean of all the sampling distributions will be equal to the population mean, which is 35%. The other thing is that we now need to calculate the standard deviation of the sampling distribution. And if I'm not mistaken, let me see if I can recall that formula, because I remember doing this recently. Let me make sure I got it down, otherwise I'll look it up. Where's my pen here? Okay, so so we got p hat has the mean of 0.35, but the deviation, I believe it's going to be the square root of p times 1 minus p divided by n, which is 0.35 times 0.65 divided by n, which was 700. I need to make sure this is right. I think it is. So that's just something you just have to have written down, or have the formula. So I'm going to add that up. Let's just type it all in. 0.65. Oh, it's actually point. Oh, come on. $35 and $65 make 1. Okay, yep. And then divide by 700. Make sure. Is it 700, right? Yeah. So I'm getting 0.018. That's tiny. See, is it right? It doesn't look right, but let's just double check. Okay, yeah, we got the formula right. And so now we're ready to answer the question. What is the probability that a random sample of 700 adults, so we're going to use the sampling distribution parameters. So what is the probability that a random sample of 700, more than 38% do not own a credit card? So this is a normal CDF problem. The lower bound is going to be 0.38. The upper bound will be some large number. So let's use StatCrunch for this. So I'm going to plug in 0.35 for my mean. My deviation is 0.018. And I want more than 38%. So I'm going to switch this around. And now I'm going to hit calc, or compute. So I'm getting, this is my probability, very tiny, less than 5%. They want me to round this to 4 places, so I'm going to put in 0.0478. Okay. So the stuff that we did in chapter 7 was important. Getting comfortable with calculating normal CDF and inverse norm, because it comes up in the rest of the sections. And then you just start to fly. You can just fly right through it, right? You just use technology. But you have to be able to interpret it. So now this time they say, hey, if 100 different random samples of 700 were obtained, one would expect, well, 100, that's 4%, so I'd say about 5. So to interpret this probability, right, what does this really mean? What it means is about 5 people out of 100, not 5 people actually, 5 of the samples out of 100 of the samples will have an average, or a proportion I should say, of more than 38%. Not many of the samples will, especially if the samples are random, which means that it's less bias, right? We're not, what if one of our samples was taken from a rich part of the country where a lot of people just have a lot of wealth, it would skew the results. So we're talking, out of all the different random samples, only 5 of them we would expect about 5 of them to have a proportion of 38% not owning a credit card. I don't know if I said cell phone or not, but let's check that. Okay, it works. What is the probability that a random sample of 700 adults between 33% and 38% don't know? Well, this reminds me, so this is an in-between, area in between. This is a normal CDF again. And we're going between 33 and 38. Remember, a lot of the samples will be between 33 and 38. Because the mean is 35. And so what we would do is just come over here and put in between, and we just put in 0.33 and 0.38, and we're getting 81, 89. Okay, another one. Let's interpret this. What does this mean? Well, it means that if we had 100, let's convert this to a percentile, we would be dealing with about 82 of them out of 100 of them. 82 of those samples would probably have a proportion of people who do not own a credit card between 33% and 38%. Then we interpret this again. Would it be unusual? Right? 5% is the critical value for being usual and unusual. That is we call it critical because it separates the good from the bad. 5%. If you're less than 5%, you're considered, it's unlikely to happen. So that's just common in 5%. The other critical value used sometimes is 1%. Depending on the severity of our tests and what we're actually trying to calculate, those are, so sometimes 10% is also considered a critical value, but amongst all of them, 5% is the gold standard. And so we would just look at this and look at the results of 231 or fewer. We see what that proportion is. If it's less than 5%, then that's considered unusual. The result would be unusual if that is. And so this is a normal CDF problem again. And we're trying to find the probability. So you put here, well, hold on. We're going from 231 or fewer. So StatCrunch can handle this. On the calculator, we'd have to put in a very tiny negative number for our lower bound. Our upper bound would be 231. Our mean and deviation will stay the same. We would get a proportion, we'd put it in here, and if it is less than 5%, which it probably is, well, would it be unusual for a random sample of 700 adults to result in 231 or fewer? Well, 231, we'd have to convert 231 out of 700, first of all. All right, 231 out of 700 is 33%. So really what they're asking us is, how many is less than 33%? So we have to use our standard curve here. And we're talking less than 33%. It's 13%. It's not unusual for some of the samples to be under 33%. In order to be unusual, it had to be less than 5%. We just got 13.3, so I'm going to put the result is not unusual because the probability of p-hat is more than. Okay, so I would say something like D. One three. We said 13333, and that is more greater than 5%. Okay. We actually calculated it out. I have it here. All right. I think this was a good start. I think what we'll do is we're probably going to wrap it up here. But I think that this was a good warm up for us for Thursday.